Let's continue our discussion of zero-state systems or zero-state responses. Previously we talked about the unit step response. There's another important signal to us. It's this exponential. So the response to an input of the form z of n. Okay. And we'll see this later in the course when we further talk about transforms of discrete time systems or discrete or difference equations. We'll run into something known as the z transform. So the z transform plays the same role in discrete time system theory as the Laplace transform does for continuous time systems. So we can find the output to this particular input, as we can for any input, by convolving the input with our impulse response, explicitly writing out the convolution sum. I can write this as the sum from minus infinity to infinity, just using m as my summation variable, h of m, and then here I have n minus m. This is the time reversed and shifted version of this input. I can factor out z of n because my summation variable is m, and I'm left with the sum from minus infinity to infinity of h of m z of minus m. So I'm going to give this thing in parentheses a name. It will actually be called our transfer function. Okay. It only depends on the particular value of z. So this is a special input because the output in response to an input of the form z of n is that same input just times, for any particular value of z, this will just evaluate to a number. So this is a very special type of input because the output is just a multiple of that input. Okay. In general, h of z might be real. In general, it may be complex. So again, where this particular case, where h of z, our transfer function, is defined by this summation, h of m z to the minus m. We'll see later, we'll call this the z transform of h of m. So our transfer function and our impulse response are actually a z transform pair. We can also show that h of z is actually equal to p of z over q of z, where, again, these were the polynomials we had from our difference equation. So if you recall, as an example, if I had something like this, plus y of n is equal to, I'll say, 3 x of n plus 1. The coefficients here make up our q function, and in the our operator notation, this would be e squared minus 2e, sorry, this should be y of n plus 1, e squared minus 2e plus 1 is equal times y of n is equal to 3e x of n. This is our Q polynomial. Okay. This is our P polynomial. So we can go directly from the difference equation to the transfer function. It would be just 3z. I replace e everywhere by z, and then in my denominator polynomial becomes z squared minus 2z plus 1. So with a little practice, it's relatively easy to go directly from the difference equation to the transfer function. And again, this will be quite important to us later in the course. We start doing system analysis via the z-transform method. Finally, putting all the pieces together on our total response. It is the sum of these two pieces, our zero state response, our zero input response, plus our zero state response, which I get by convolving the input with the impulse response of my system. So in general, our zero input response consists of a number of modes depending on the order of our difference equation. Here I'll just assume all the modes are discrete and real, and then so in this portion of our response we call the zero input response. It depends only on the initial conditions. It doesn't depend on the form of the input at all. And this portion of the response we call the zero state response. It's the portion of the input that doesn't depend on the initial conditions at all. It assumes that the initial conditions are all zero, hence the term zero state response. This gives us the output component that's due to the input.